Hi, and welcome to the next section in our chapter on boosting, which is a simple subsection on regularization, where we'll learn about three main regularization options. So controlling the number of iterations, controlling the tree depth if we are using trees as base learners, and via the learning rate, or sometimes people also call that the shrinking parameter of boosting. And you want to understand a bit more how regularization influences model fit. Most of the things we're going to discuss here won't be super surprising and super difficult to understand. So there are a few more technical details when we later on talk about boosting with trees specifically in another subsection, and if we discuss component-wise boosting, or rather XG boost. But here this subsection is mainly mentioning obvious ways of regularizing the boosting machine. I guess for completeness sake, and to see a few more examples and to get a better feeling for what the effects of these settings are. So let's start. So first of all, it's important to state there has been a longer historical discussion, which is, I guess, from my perspective now rather really interesting from a historical perspective, whether algorithms like boosting and bagging can actually overfit. And for bagging, the answer is much more so into the direction that it's very hard to overfit with bagging, like in a random forest, with respect to increasing the number of the number of ensemble iterations or ensemble members. It is still possible for that to happen in a model like the random forest, but due to the effect of variance reduction, which is the main effect of increasing ensemble size in a bagging model, this is usually very hard this is usually very rare that this happens. Okay, in boosting, this is a bit different because we do this iterative backfitting against residuals or pseudo-residuals, which really results in aggressive loss minimization. So overfitting can clearly happen if we let the boosting algorithm run for a long time. Now, I already mentioned our options for regularization, so we can simply limit the number of iterations. So this what we called here the capital M parameter, and that simply limits our number of additive components. We could also call that early stopping in the algorithm. And very often this is also achieved by peaking into a validation set and seeing when validation error does not go down anymore or even goes up, and then to early stop at that point. We can also limit the number and the depth of our trees. This can also be interpreted as choosing the order of interactions, but we have special subsections on boosting with trees because this is such an important combination, and there are a couple of technical details to consider. So I'll discuss this at another point more in depth. Or, as always, that's also pretty normal and regular, a common regularization technique. We can control the learn rate alpha and only do mild model updates. And some people also call that the shrinking parameter in boosting because there are some connections to shrinking, parameter shrinking and penalty techniques, which I will not discuss here in this section. So some practical hints. So first of all, it should be very clear that the optimal values of M and alpha strongly depend on each other, right? So if we do more iterations, we can use a smaller value for our learning rate and vice versa. So if we only do a few iterations, we probably have to use a higher learning rate. And it's quite obvious that setting the one parameter will influence a good or optimal setting of the other one. A fast option, and that's often recommended, especially in the statistical literature with respect to algorithms like component-wise boosting, which we'll discuss at a later point, is to make alpha small and then choose the number of boosting iterations by some validation set technique like cross-validation. I usually, when I do practical work with boosting, try to tune all three hyperparameters with an efficient tuning technique. So can run some more or less efficient algorithm like grid search, random search, or even Bayesian optimization on all three hyperparameters. And the larger our hyperparameter space would be, the more we would be inclined to use a more efficient technique, and then be pretty sure to find the hopefully optimal configuration of all three settings. There's also stochastic gradient boosting. That's a further regularization technique. Some people also call this row subsampling in boosting. So this is really a minor modification. The idea is to kind of incorporate a bit the advantages of bagging, but be a bit careful here. I mean, the whole algorithm is not bagging, because we still are doing this iterative reduction of residuals. What we now do in each iteration is that we only fit on a random subsample of the training data in each iteration. So we just, I don't know, subsample 70 observations and do the pseudo-residual fitting on this subset. And this especially helps for small training data sets, for noisy data sets. It can also be a good technique for larger data sets, but in the literature, it says, I guess more the effects, the positive effects have been more visible for small scale problems. It's usually nowadays a pretty regular available setting in most boosting implementations. Of course, this introduces now a new hyperparameter, which is the size of these random sets. Here's an example I think we have seen before. So you can see here a simple sinusoidal function. It's just a sine with some Gaussian noise. So on the left-hand side, there is no noise. On the right-hand side, there is, with a standard deviation of 0.2. And you can see that, I'm using trees here, tree stumps as a base learner, and you can see that we can actually fit quite nicely through this noiseless sine function. But on the right-hand side, you can really see how we are beginning to overfit for larger numbers of boosting iterations. So if I use 1,000 iterations, I begin to basically, not exactly interpolate, but getting close to interpolating all of the noisy points here, which is what I don't want. And what is this? Exactly this result of the aggressive loss minimization and boosting. Here's a short, simple 2D example with respect to the learning rate parameter now. So I'm using the spirals data set here in 2D. As you can see, these intertwined two spirals. And we now examine the effect of the learning rate and keep the number of trees fixed, and also keep a fixed tree depth. Here you see a very, very small learning rate in the software that we're using here. This is now, like I said, called the shrinkage parameter, which is just an alternative name for the learning rate. Here we have a medium setting, and here we have a very, very high setting. I use some really extreme settings here just to make a point and see, and to get a better understanding of what happens if we change that parameter. We can really see that we now have an over-smoothing effect in the left scenario here. So here we do tiny, tiny, tiny baby steps, and we really regularize our model quite heavily, which means we'll never really end up in a parameter state or in a point in our hypothesis space where we can model this spiral shape here very well. So we just get that really bad stripe landscape in our resulting model. So I guess we would call that a clear instance of underfitting. With the medium shrinkage parameter, it works quite well. And here you see also pretty strong overfitting if we do these large step sizes. Further example, which is now a bit more higher dimensional than just 1D or 2D. So this is the spam detection data set. This is a slightly imbalanced binary classification data set with, I think, about, can't remember exactly, a few dozen features. And we use, because it's binary classification, we use the Bernoulli loss. We use different numbers of iterations. So from 1, I guess 0, we don't really use. So I guess we either use 1 tree or up to 10,000. Here's our learning rate. We try 3 different settings for that and different tree sizes. Tree depths. And as I said, you can also see this as a parameter that controls the number of interactions that we are modeling between features. And I'll discuss this more in depth later. And you can see here now pretty unsurprising effects of these 3 parameters. You can also see somewhat how they interact or interplay with each other. So here in the faceting, you can see different settings of our shrinkage. So again, very low up to very high. So this should lead more to underfitting. This should potentially lead to faster overfitting. But we can also now see on the x-axis the number of iterations. So, and on the y-axis, you see our misclassification error. I have evaluated that with a 3-fold cross-validation. So this is not a nested setup here. So you kind of see the validation error as it develops when we change these 3 hyperparameters in a grid search over this parameter space here. We have also marked the optimal configuration in red. So this is a part of this yellow line here. And you can see that this is here. I guess you could argue that as we are on the boundary of our hyperparameter space, I should have probably run the whole thing again with a larger hyperparameter space, because there might be a better value somewhere else beyond our ranges. Out of laziness, I didn't do that here, because I'm also really not looking for the optimal configuration now on the data set. I just want to discuss the effects of these 3 parameters a bit. And so what can we see now? So first of all, we can see that let's maybe look at the color coding of the lines first. So that's the tree depth, or the maximal tree depth we are allowing in our ensemble. So 1 would mean no interactions between features, and we go up to 20, which is quite high. And you can see the higher the tree depth, the faster we learn. And for this small shrinkage here, that's actually a good thing. But if you begin to go to higher learning rates, you can also see that if we are not careful here, we can also quickly overfit with these very, very deep trees, and sometimes we can overfit quite quickly. I guess with the number of iterations is also clear. We see this usual U shape, especially here and here. So the more iterations we use, so in the beginning, we go from underfitting to a better model fit. But at some point, we hit that U shape here. And then validation error goes up, because we begin to overfit while we are adding in more components into our ensemble. And again, the lower our learning rate is, the later that overfitting behavior happens, and vice versa. Now, I guess, especially for this shrinkage parameter and for the tree depth, it's not so problematic that the stuff begins to overfit, because we can see that in our validation error and then kind of try to figure out the optimal setting. A problem is if we set that so high that this begins to happen kind of too quickly, and that we kind of overshoot that optimal point and we can't really see it that well during optimization. So that might be a problem. But in general, there are multiple heuristics now. I already mentioned one. So use for shrinkage maybe something like this here, so a small value, and then just change the number of iterations. And I guess the tree depth you somehow have to guess or whatever. This is possible, or you can also look at these plots. Usually I would recommend, especially for more complicated situations where you really also care about optimal prediction error, to do proper tuning, which we also discuss here in this lecture, how to handle that.